take a look at graphing transformations of trig functions, but we're going to focus on tangent, cotangent, secant, and cosecant. So let's take a look at sine and cosine. Just remember what those look like. Okay, while that's coming up, does anybody remember what sine and cosine looked like when you graph them? Are they a straight line? Do they look like a parabola? Yeah.
Aren't they waves?
Yeah, they look like a wave. Like I have one on here right now. That's cosine. It looks like a wave. And if we remember, the highest was 1 and the lowest was -1. But it went forever left and right. Okay, so it looked like a wave. Well, with tangent, it's going to look a little bit different. Okay, it doesn't look like a wave. So let me show you. Let's see. Let me show you what tangent looks like. So let's put in tangent. Hit graph. There's definitely a pattern to it, like sine and cosine, a pattern that repeats, but it's not a wave at all. What do you notice here that looks completely different? Like if you wanted to draw it with sine and cosine, you could just draw the whole thing without ever doing something. But here, you have to keep doing something. Yeah?
You're going to have to eventually lift your pencil.
Yeah, and whenever you have to lift something and then go back down to draw the next section, what does that mean you have in your graph? Or if you look at this one, what does it look like it has in it? That sine and cosine did it, yeah?
Holes.
There's no holes in this one, but a hole is a time something you have to lift it, put it back down again. But this is a different reason why we have to lift and start our graph again. Not a hole. Yeah?
Isn't it asymptote?
Yeah, we have asymptotes. So the graph of tangent has asymptotes at very regular intervals. Okay. So let's draw on here just one section of tangent. So to figure out where the asymptotes are, they always occur for tangent and cotangent on multiples of 90. You have to figure out which multiples of 90 though. It's not every single multiple of 90. It's more like every other multiple of 90. So if you go to your table and start with 0 and try that one. Okay, 0 works fine. So 0 is not an asymptote. What's the next multiple of 90 after 0? Ashley?
Not sure.
So next multiple of 90? 90, yeah. So let's just try 90. Now that one we got an error, right? So now let's try the next multiple. What's the next multiple of 90 after 90? Yeah? 180. So that one's probably going to be fine because it's every other. And then what's the next multiple of 90 after that? Yeah? 270. So that one's not going to be fine. So you get asymptotes every other multiple of 90, starting at 90. So I've got the same thing here. I'm just going to do it in radians. So pi over 2. That's 90. And what was the other one we had? 270. That's 3 pi over 2. And if you wanted to keep drawing, you could just keep drawing asymptotes left and right forever. Now let's look at what happens near the asymptotes. Usually what happens is the graph all of a sudden starts to curve up forever, or it curves down forever. Let's try a value a little bit bigger than 90 in the table and just see what happens. Somebody give me a value that's just a little bigger than 90, but very, very close to it. Yeah?
90.000001.
Yeah, this is pretty close. So 90.0001, and you can see what happens. We're way, way down at like negative 572,000. So the point is, when you go just a little bit bigger than 90, the graph all of a sudden drops way down. I know that's not negative 572,000, but that's the best I can do. Okay, it goes way down. Now, let's try a value. Well, we already put pi. 180, that's pi. So I know the graph goes right through there. And then let's try a value very close to 3 pi over 2. That's 270. But just before 270. Yeah?
269.999.
All right, so let's try 269.99. Just 269.99. And you can see when you type a value very close to 270, but just before it, your graph is up over 5,000. So all of a sudden, when it gets close to that, it goes way up. So we need to connect those 3 dots, and that's basically what tangent looks like. Okay? But remember, all trig functions usually have some type of smooth curve to them. So we shouldn't be drawing anything that's like a straight line or anything that has like a point on it. Okay, so we've got to stay very close to this asymptote. But we have to start thinking about curving to get to that point because we know it goes through 0. Because I checked that on the calculator. Okay, it goes through 0. So it's going to come up. It's going to start to curve, but it can't keep curving because it's going to run into another asymptote. So all of a sudden it's going to curve, but then it has to curve back again. And that's what your graph of tangent looks like. So what I drew on here was this second section. And if you copy and paste it, that's what the graph would look like forever. So actually I drew it in 2 pieces, so I'll just draw it again. Here's the next cycle of tangent. Looks just like that. So now you're looking at 2 cycles. Yeah.
What equation did you plot on the calculator to get those cycles of tangents that are on the calculator?
Just tangent. Just tangent.
Okay.
Remember, when you graph something on the calculator, we usually have to do zoom 7 because that'll set the window to a trig window. If you don't do zoom 7, it might not look right. If we have to adjust it, we'll adjust it. But zoom 7 is it's kind of a good starting point. Hey, any questions on that? What it looks like? The other thing we have to kind of think about is what the period of this is. Does anybody remember, this was a while ago, but for sine and cosine, you had to go from 0 to how much to go through one full cycle? This would be 0. Where would the cycle end? If you don't stretch it or compress it, where would it just naturally stop? Yeah?
360 or 2 pi.
360 or 2 pi. Yes. That's the natural cycle length for sine and cosine. Let's see if we can figure out what the natural cycle length is for tangent. Let me set my window to go between 90 and 270. The reason I'm going to do that is so I can just focus on one section. So let's go 90 to 270. Now, I kind of already said this, but how many sections am I looking at in that window?
2.
Well, on the graphing calculator. Not what I drew.
1.
1. Okay, we're looking at one section. And where does the left edge of this window start? Yeah?
Pi over 2.
Pi over 2, which is
90.
90. And where does the right edge of the window stop? 2 pi would be over here. So if we set it at 2 pi, you would be seeing 1, plus you'd be seeing part of another cycle. So it doesn't go as far as 2 pi. Yep.
Stops at 180.
If it stopped at 180, that's pi, you would only be seeing this bottom section. So it goes further than pi. Yep.
Subset 3 pi over 2 or 270 degrees.
Right. So it starts at 90, it stops at 270, and that's one cycle. How wide is that? 90 to 270. Yeah?
180 degrees.
That's 180 degrees. So for tangent and cotangent, which you'll see in a minute, one cycle is 180 degrees. That's different than sine and cosine. The period of tangent and cotangent is pi, not 2 pi. So if I put a box around what one period looks like, that is what one period looks like. Now, what we have to do is decide how many asymptotes there are per period, per red box. Here's the next period. Right there. So I've labeled the first period on there, and then the second period. Each period has to have the same number of asymptotes. Otherwise, it's not periodic. It all has to be the same all the way down. So how many asymptotes are in box 1? If every box has to have the same number of asymptotes all the way down. Yeah?
Isn't it 2?
Okay. So then you're saying,
Or would it be 1?
so if we say, well, let's start with 2. Let's label these asymptotes. This is asymptote 1. This is asymptote 2. That's asymptote 3. So you're saying asymptotes 1 and 2 would belong to box 1. So then what belongs to box 2?
Just 3.
So now that's a different number of asymptotes than the first box. Remember, an asymptote can only belong to one box. Can't be in 2 boxes. So, anyone else have any other thoughts about that? Yeah?
They get 1.
They each get 1. It doesn't matter how you think of which one it gets, but it's kind of like the idea of like armrests. Like you share armrests, like a theater or something. You don't get both. All right, you get 1. So you either think of it as like, okay, this box gets the one on the left, and then every box always gets the one on the left, and that ensures every cycle each has the same number of asymptotes. If you say box 1 gets 1 and 2, well then what does that leave for box 2? Now it only has the 3. It doesn't have 2. It doesn't have 2 asymptotes. Okay, so there is 1 asymptote per cycle, and that's why I put a box around this. Pi over 2 is the asymptote in the first period. This 1 here goes with that 1 right there. 3 pi over 2, that asymptote I would say belongs to the second box. And then 5 pi over 2 I would say belongs to the next box, which I didn't draw. Okay, so a couple things just to kind of understand there about how tangent works. Now, what's the connection? We're going to look at cotangent now. What's the connection between tangent and cotangent? Remember, yeah?
Is cotangent the reciprocal of tangent?
Yep, it's the reciprocal. All you do is flip it. Right? You take 1 over tangent, that's your cotangent. Since tangent and cotangent are reciprocals, they are going to look a little bit similar. Let me put, I'm going to go like this and like that. Put tangent and cotangent on the board at the same time. So on the left, you're looking at tangent. On the right, you're looking at cotangent. What's the difference? Or yeah.
It curves up on the left and down on the right.
All right. So cotangent always has a negative slope. It always has a negative slope. Like if you were standing on part of this, it's going down to the right all the time. Where tangent is always going up and to the right. Now, we could change that if we did like a reflection or a transformation. But I'm just talking about the regular tangent and the regular cotangent. Okay, so it does curve down to the right. What's the same between these two graphs? What's something that they both have in common? Yeah?
The period.
Yeah, they both have exactly the same period. If I just put a box around this cycle right there, that box starts at 0, and it ends at pi. How much is pi? Yep.
180.
180, yeah. So the period here is equal to pi. So yeah, same period. What else do they have in common? Yep.
They both have one asymptote.
Yep. First, I was going to ask what if something even more general. They just have asymptotes, but even more specifically, they have one asymptote per period. Same idea as tangent. You can't say that two belong to the same cycle because then it doesn't leave something for the next cycle. And if you want to graph that one on the calculator, as Declan said, it's the reciprocal, so you have to type it in as 1 over tangent. And let me do zoom 7 so you can see a lot more. The other thing, if you look carefully at them, tangent, I didn't draw this cycle, but tangent does go right through the origin if you drew in the cycle before the one that I drew. Cotangent does not. It skips the origin. So let's look at one other thing that they kind of have in common. Let's write down the values where it crosses the x-axis. Where does tangent cross the x-axis? What's the first one that I drew? Yeah?
Crosses at pi.
Pi. Yeah. What's the next place it crosses? Let's see. 2 pi. Where do you think the next place it would cross would be if I drew it, but I didn't? Yeah? 3 pi. And it would cross at 0, but I didn't draw that one. Now, let's write down the zeros here. Where does cotangent cross? Yeah?
Pi over 2.
Pi over 2. Where would be the next one it would cross?
3 pi over 2.
3 pi over 2. And the next one after that would be 5 pi over 2. So these are where it crosses the x-axis. Now, these are the zeros for tangent. Look at all these numbers on the cotangent graph. What do you notice about 0, pi, 2 pi, and 3 pi on the cotangent graph? Yeah?
Those the asymptotes.
Yeah, those are the asymptotes. The zeros for the tangent are the asymptotes for the cotangent. Now, let's look at the same thing here. These are the zeros for cotangent. Pi over 2, 3 pi over 2, 5 pi over 2. What do you notice about the zeros for the cotangent when you look at them on the tangent? Yeah?
They're the asymptotes.
They're the asymptotes. So what happens between the graphs of tangent and cotangent is the asymptotes and the zeros switch. All the zeros for tangent become the asymptotes for cotangent. All the zeros for cotangent, you're welcome. All right, so you guys already kind of figured this part out, but the period of tangent and cotangent is pi, and we already wrote that down. So remember what that means. Period means that's the amount of time you have to travel before you're going to get exactly back to a point you started at. So let me type in, for example, tangent of 10. And I get that answer. That exact answer is going to occur again one cycle later. What's the length of the cycle in degrees for tangent? Yeah, 180. So that means if I take 10 and I add exactly one cycle to it, it gives me back exactly the same answer because I'm at the same spot one cycle later. If I took tangent of 10 and I added 2 cycles, what do you think I would get when I hit enter? Yep. I'm going to get the same thing because I'm looking at the same spot again. Now I'm just 2 cycles down from where I started. So the point to that is you can take the tangent of a number, or you can take the tangent of that number plus any multiple of 180, and you'll get exactly the same thing. And if you say, well, what about subtraction? Yep, you could also subtract and go one cycle earlier. And if you're wondering, well, why didn't I write plus or minus here then? Because n is an integer. So if I wanted to represent subtracting a multiple of pi, just let n be -1. Then this would say x minus pi, or -2, -3. But the point is, you can add any integer multiple of pi, or 180, to the value of tangent, and you'll get the same thing back. You can't add, like, half a multiple of pi, because that only brings you halfway through the cycle. You either have to add an entire cycle, or subtract one entire cycle, which means add or subtract 180. And you can do the same thing for cotangent. Yeah?
When you say multiple of pi, you mean 90, 180?
Yeah, so if you're doing degrees, it'd be like adding 90 times 1, 90 times 2, 90 times 3, 90 times 100. As long as you add a multiple of 90, or subtract a multiple of 90, this formula works.
So n could be like 30?
Yeah, you could add 30 multiples of 90, and that would give you the same answer 30 cycles down the graph.
But it couldn't be like 7. Could n be like 7?
Yeah, then you'd be 7 cycles down. What you can't do is like 7.2. Now you're in between cycles. You either go a whole cycle or you don't go a whole cycle. You can't go like a quarter of a cycle.
So does n represent the cycle or does pi represent the cycle?
N represents how many cycles, and pi represents the length of each cycle. But n specifically represents how many cycles. Think of n as like, it's an integer. It's a number that's not a decimal. It's like going to the store to buy a can of paint. You either buy a can of paint or you don't buy a can of paint. You can't buy 1.2 cans of paint. If every can is the same size, you buy the can, you don't buy the can. You can't buy half a can. So we've talked about transformations. Putting a number in front, putting a number on the end, all the different things we can do. When we're working with tangent and cotangent, every transformation we already know is exactly the same. So if you have a problem that involves multiple transformations, we know there's an order of operations. You have to do them in a certain way. The A, B, C, and D represent the order that you would have to do the transformations in. If you had more than one in the same problem. Just because it's easier for me to go left to right, I'm going to start with C and write down each one of them that way. So C is multiplying by a number in front. Does anybody remember what kind of transformation that is? Multiply by a number in front. Yeah?
Is that one a horizontal stretch? Or is that one the vertical stretch?
That's your vertical stretch. Yeah, horizontal is always inside the parentheses. Vertical is outside. So C is a vertical stretch. And what happens if C is negative? What would that cause your graph to do? If it was negative 5, it would be a vertical stretch by a factor of 5, but then the negative would, it would flip it. Which way would it flip it? Yeah?
A reflection on x-axis.
A reflection over the x-axis, yes, which is vertical. So C would do something like this. That's a vertical reflection. Right, let's keep going. Let's do B next. So B, it's still multiplication, like C, but now it's inside. Yep.
That was the horizontal stretch.
That's your horizontal stretch. And remember, horizontally stretching changes the period. So we can lengthen the period by stretching it, or we can shrink the period by compressing it. So this is your horizontal stretch. Remember, B is the opposite of what you would expect. The bigger you make B, the more compressed your graph gets. So for example, here's cotangent. Let's put a bigger value in front of x. Let's put in like a 3. The bigger we make the number in front of the x, the more compressed the graph gets. And when it starts to get too compressed, the calculator has a hard time drawing it. So that's not at all what it really looks like. All of these should continue up and down forever. But because we've squished it, it got too steep for the calculator to know what to do. And there shouldn't be a gap like that at all. Should be connected. You might be able to change how it looks a little bit if you put detect asymptotes off. I don't think it's going to look better. Actually, that one didn't help. I didn't think it would, but there's not much I can do to make that graph look the way it should. Okay, so that's B, and just like C, if it's negative, that's a reflection. Okay, how about A? What does that do? Adding inside parentheses, yeah?
That's a horizontal shift.
That's your horizontal shift. We also call it a phase shift when we do trig. That's your horizontal shift. And remember, that is backwards. So if you add a number inside, which way is that going to move it? Yeah? Left. If you subtract a number, right. And what about D? Yeah? That's your vertical shift. So no difference between all the ones we've done before and what we're doing right now. Okay, so any questions on what the A, B, C, or D do? Yes?
Is that vertical stretch for C, is that the same thing as amplitude, or is that a different?
Well, the thing with tangent, or cotangent, when you talk about amplitude, you're talking about how high and low something goes. Tangent and cotangent go up and down forever. So their amplitude is really infinite. So they don't really talk about amplitude with these kind of graphs. Amplitude makes more sense when there's a definite high and a low, but a high and low here is infinite. All right, so we had a period, we had a formula last time to find the period of sine and cosine, and the formula was 2 pi over b. 2 pi over b. Well, for tangent and cotangent, a little different. It's pi over b. The reason why it's pi is because whatever you put in the top of that formula has to be the original cycle length. If the original cycle length is pi, you put a pi. If it's 2 pi, you put a 2 pi. So that's why with sine and cosine we use a little bit different formula. I'm going to come back because there is something else I want to write down on this page, but it's going to make more sense to write it down after I show you something else. So I had it in the notes next, but we'll come back. Okay, does everybody have that formula? Okay, so this question basically is going to use the formula I just gave. Find the period of tangent 2x and find a graph on the calculator, don't do it by hand, just do it on the calculator, that shows exactly 3 cycles. Now, if you break a cycle in half, that is okay. Like, if your window looks like this, that's good, that's 3 cycles. Or, if it looked something like that's also 3 cycles because you've shown a half, and 2 in the middle. Sometimes, depending on how you set your window, you might break a cycle in half. That's okay. All right, tan 2x. Okay, why they use the t, I don't know. That's just the formula they use for period. But what's the formula for finding the period of tangent? Lucas?
The pi over b.
Pi over b. Now, if you're wondering, well, where does b come from? B is the number that's in front of x. That's where b comes from. Okay, so in our case, what is my b value? Yep.
2.
2. Now, b is not the period. B is just b. The period is when you put b in the bottom of the fraction, pi over 2. So that's the length of one period. But on the calculator, they want me to show 3 for whatever reason. They want to see it 3 times. If that's the length of one cycle, how long is 3 cycles going to be? Yep.
3 pi over 2.
3 pi over 2. If this is the length of 1, and they want you to show 3, then you need to triple this length. So to show 3 cycles on the screen, we need to set a window from 0 to 3 pi over 2, because that is 3 cycles. All right, so first thing, because we're dealing in radians, pi over 2, that's a radian. Let's put our calculator in radians. Now, the only condition here is to show 3 cycles, you need to set a window that's 3 pi over 2 units wide. There's lots of ways to do that. I think 0 to 3 pi over 2 is the easiest. It's like if I said to you, set a window that's 10 units wide. You could do 0 to 10. You could do 30 to 40. That's 10 units wide. You could do 100 to 110. There's lots of ways to make it 10 units wide. But I usually start with 0. Okay, let's put a tick mark. I'm going to change the X scale, because I usually just like to see a tick mark every 90 degrees. The tick mark isn't really important. You can don't even change it if you don't want to, but I changed it. Okay, let's put our graph tangent 2x. Let's get rid of that and make that a 2. So if we did this right, we should see exactly 3 cycles. Looks like we did break one in half, but that's okay. So there's 2 in the middle, half on the left, half on the right. And that is a graph of 3 cycles. Would it be nice if they were all connected? Yeah, you could shift your window a little bit so you could see them as connected. But if you show that, that's fine. So what they'd ask you for on the homework for that is just to write down the window. And there's your window. X min, X max, Y min, Y max, that's what I'm looking for. It doesn't really matter the Y min and max because it's going up and down forever. So, I mean, negative 4 to 4, that's plenty. Negative 10 to 10, that's also fine. Questions?
There isn't like an exact answer, right? As long as you're setting those 3 and
Yes. Yep, correct. There is an exact answer for the period, pi over 2. But as far as your window, there's lots of answers. And what we're going to want to be able to do there is figure out where the asymptotes are. And you might say, well, yeah, but for tangent, we already figured out where they are. They're right here. Pi over 2, 3 pi over 2, 5 pi over 2. Not if you compress it. If you compress or stretch it, you're changing all these asymptotes. So, well, we have to talk about how you find them. Okay, so here's a problem that basically it's just kind of like an identify. It might be like a matching problem. One of these is the graph of 2 tangent x, and one of them is the graph of 5 tangent x. I just want to know which one is which. So this basically requires you to know what the 2 and the 5 are doing to be able to identify which one is which. Let's look at the one on the left. Which one do you think that is? Is that the 2 tan x or 5 tan x? How come? This 5 is not doing any kind of compression.
But if it was in the horizontal, it was. Oh, wait.
It's not the horizontal, yeah. Yep.
So vertical stretch.
Right. This is a vertical stretch by 5. So which one do you think it is?
First one.
Yeah, it is the one on the left, but it's because you've taken and stretched it vertically. Okay, imagine you had like a metal rod that was curved like that. And you put the ends in something and you pulled on it. Well, it would start to straighten out. So that's what's happening on the left. So the one on the left is stretched vertically more than the one on the right. And that's all you have. Now, if I asked you to identify the asymptotes in this one, there's no change to the asymptotes here compared to the original. Stretching vertically does not change asymptotes. Stretching or compressing horizontally would change it. Any questions on that? All right, let's take a look at the graphs of secant and cosecant. let's think about cosecant for a second. How would you type cosecant in on the calculator? Yeah.
1 divided by cosecant.
1 divided by
Sin.
yeah, sine. So 1 divided by the sine. Now think about sine for a second. Sine looks like that. Does sine ever cross the x-axis?
Yes.
Yeah. And where something crosses the x-axis, like here, here, and there, what's the y value? Yeah?
0.
0. So what I'm basically saying here is the graph of sine can equal 0. Sine of x can equal 0. What happens in a fraction if you put something in the bottom that could equal 0? I'm not saying it's always 0, but it could be sometimes. Yeah?
You're saying that it can't be 0.
Well, no, I'm saying, so what happens if you put a 0 in the bottom of a fraction?
Doesn't work.
What do you get?
It's not like a thing.
It's not a thing, right?
You just don't do it.
Yeah?
Oh, never mind.
So if we try to divide by 0, it's undefined. You can't do that. So what do you think that's going to look like on a graph? If you try to graph something that's undefined. You can get very close to undefined, but you can't reach it. Yeah?
You can have a hole.
Well, a hole would be one possibility. What's another possibility? Yeah?
It just never touches the x-axis.
Well, it's never going to touch something. And what do we call that thing that it would never touch? Yeah? No? Yeah? The asymptote. So just like tangent and cotangent, cosecant is going to have asymptotes because this is the formula for cosecant, and this value can equal 0. Like there is a point where sine crosses 0. If it never crossed 0, then we wouldn't have any asymptotes. But it does, so we do. Same thing with secant. Secant is 1 over cosine. Well, the graph of cosine also crosses the x-axis, which means there are points where this graph hits 0. And if that ever hits 0, and you try to graph it, you're going to end up with a fraction with 0 in the bottom, and you can't do that. That causes asymptotes in your graph. So let's take a look at secant. So that's what secant looks like. It's kind of like these U shapes and N shapes. This is one cycle. One U shape, one N shape. And if you keep copying and pasting those U and N shapes, that's what it looks like. And if I just kind of, it's not very good here, just finish that one up. Put one more. That's my second cycle. Okay, so how many asymptotes do you think there are per cycle in this one? This is box 1. That's box 2. And we could label these asymptotes 1, 2, 3, and 4. Which asymptotes belong to box 1? Yeah?
1 and 2.
Yeah, there are 2. However you want to think of it, each box gets 2. Whether you think of it as the 2 on the left or the 2 on the right, each box has 2.
My question was going to be, could it have the ones on the right? So could it be 2 and 3?
Yeah, that's just a mental thing, how you think of it. We don't normally draw boxes on the graph and separate it into cycles like that. But yeah, however you want to think of it, there are 2 asymptotes per cycle. And that's the same for secant and cosecant. So we saw tangent and cotangent looked pretty similar. So do secant and cosecant. And if you look quick, you might say, oh, well, they're exactly the same. But they're not quite the same. Can anyone describe to me what's different between the 2 graphs? Yeah?
It's flipped.
What do you mean by that?
Well, like on this graph, the like top of it is, I don't know how to explain this, but it's like down, up, down, up, and then it's up, down, down.
Okay, so yeah, depending on where you start from, you might kind of see a different starting point, whether it's up or down. Here's another question. How could you turn this one into that one? Look at what you could do with the one on the left, and it would become the one on the right. Yeah?
The cosecant starts right next to 0, and the secant flips 0.
So yeah, the secant goes right through the axis, the cosecant doesn't. Cosecant never touches the axis. These are horizontal shifts of each other. If you took, just like sine and cosine, if you remember, they are horizontal shifts of each other by 90 degrees. That's exactly what these are. If you take the graph on the left and you bump it 90 degrees to the right, this graph turns into that one. That's the difference between them. They are horizontal shifts of each other. And if you look at the one on the left, I don't have the tick marks in the right spot for this one, but this first asymptote, what I call asymptote 2, that is at pi over 2. Asymptote 3 is 3 pi over 2. The next one is 5 pi over 2. That's where the asymptotes are. The next one would be 7 pi over 2, 9 pi over 2. So it's getting to be a little complicated now to keep track of all these asymptotes. So what we're going to do, we're going to put them all on a table so we can remember, okay, what are the asymptotes for tangent? What are they for cotangent? What are they for secant? And what are they for cosecant? Okay, for cosecant, we start at 0. The next one's at pi. 2 pi, 3 pi. But the idea is not to list out every single asymptote because there's infinitely many. All you have to do for secant and cosecant is list 2 of them. Because I know after that, every asymptote is just going to be a repeat of the first 2 you told me. One cycle later, or one cycle earlier. Okay, somebody remind me again, what's the formula for cosecant if you wanted to type it in on the calculator? Yep. 1 over sine. And what was the period of sine? It's one of the first questions I asked today. Yep.
2 pi.
2 pi. Yep. 2 pi or 360. Secant and cosecant are just the cosine and the sine flipped. So if you want to find the period of secant or cosecant, you're going to use the formula 2 pi over b. So now we've seen all 6 trig functions. You use 2 pi over b when you want to find the sine, cosine, secant, or cosecant periods. The only time you use pi over b is when you're dealing with the tangents, tangent or cotangent. And I put absolute values here. I don't think we're ever going to have an example where b is negative. That would be a horizontal reflection. But in general, most of the problems I give you already have b as a positive. Okay, everybody have that formula? Okay. So let's put all the information about asymptotes in a table, and then I'm going to go back to what was on this slide. Okay, let's start with tangent. How many asymptotes did we say were in one cycle of tangent? Yeah, just one. And what was the first positive one that we had when we did tangent? Yeah, pi over 2. Okay. That's all you need to know to figure out where the new asymptotes of tangent are going to be. That is going to be explained right below this table. That's what's going to be on this slide. But I wanted to put that with this. So to find the new asymptote, you take and use the old one. And the old one is going to help you to calculate something. That's what I need to explain to you what to do. But once you know what to do, you just have to put plus the period times n. Whenever you put plus the period times n on something, that represents it repeating every single period forever. Now you don't write the word period, you put the period in. It's either usually going to be a pi or a 2 pi. But you have to fill that in. Okay, let's go to cotangent. How many asymptotes were there per cycle for a cotangent? Yeah? 1. And what was the first asymptote that we talked about when we looked at the graph of cotangent? It's the left one of that red box. Yeah? 0. That's the first one we talked about. So for cotangent, to find your new asymptotes, you're going to do something with the old one. It's going to give you a value. And then you have to put plus the period times n to represent that value repeating forever. Okay, how about secant? How many asymptotes did we say happened in each cycle for secant?
2.
2. Let's go back and look at the picture and identify the first 2. Pi over 2, 3 pi over 2. That's what's going to go in that box. And then you're going to do something with the pi over 2, and that's going to give you a value. And then you're going to write down plus the period times n to tell me that that value repeats forever. And then you're going to do the same thing with 3 pi over 2. The thing you have to do to get this value, it's very simple, but he's not told you what it is yet. And what about cosecant? How many asymptotes did we say happened per cycle in cosecant? 2. I'm not going to go back to the picture, but if you go back to it, you'll see the first 2 are 0 and pi. You're going to do something to the 0, and then put plus the period times n, and then you're going to do something to the pi and put plus the period times n. I could go like this. I'm about to explain to you what you do to get all of those. It's the same thing for each one. Everybody have that too? So, how do you find the asymptote? And what I'm about to tell you is general for any trig function. So this works for the tangent, the cotangent, secant, and the cosecant. Well, the first step is already done for you. If you wrote down that table, you already know all the asymptotes in one period. It's the left-hand side of that table. So that's done. Now, what ends up changing the period is when you do something horizontal to it. Either stretch or shift. That's what can mess up your asymptotes. That's the horizontal stuff. Vertical stuff doesn't do anything to asymptotes. Shifting up and down or stretching. Okay, don't worry about that. Just what's inside the parentheses. So step 2 is to take the original asymptotes that you already have on the left-hand side of that table and set them equal to, you can put a blue box around it, set them equal to the argument and solve. Argument is what's in that blue box, bx plus a. And step 3, you've already written down. Step 3 is the right-hand side of the table. Well, I guess still step 2. You have to take what you got from step 2 and put plus the period times n. So I drew a box like this on the table I just gave you, and I put an arrow and I said explained below. This is how you get that number. You do step 2. Set the original asymptote equal to the blue box, the argument, and solve. We'll try an example of that. Okay, and we're just, whatever we get to in 6-4 today, that's just what we get to. If we don't quite get to the whole thing, I'm not going to rush to get to it because we have an extra day this week. So if we have to finish it tomorrow, that's fine. And you don't have to memorize that table either. You can use that table on a test on Friday if you want to put it on your reference sheet. Might be helpful to have it. So step 2 is how you figure out those things in the box. You guys have all that on the same page, so I think that'll be a little bit better. All right, so let's try it. So let's find 4 things: domain, range, period, and vertical asymptotes. And it's just secant. I'm not even doing a transformation to it. Okay, I'm just going to start out with just secant. We'll go back and look at the picture to kind of help us. Start with the period. What's the formula for the period of secant? Is that the pi over b or the 2 pi over b? One of those two. Yeah.
T equals pi over b.
If we're doing tangent or cotangent, yes. What about for secant? Yep. That's the 2 pi over b. So the other one's still a good formula, just not the one we need for this one. What's b in this case? Since there's nothing in front of x. Yep. It's just 1. So 2 pi over 1. So there's a period. Let's do range next. I'm going to go back and look at the picture of secant and see if we can figure out the range. Now I'm going to erase all this just so it looks a little cleaner. Okay, look at secant. Does it go up forever?
Yeah.
Does it go down forever? Does it hit everything in between going up and down forever? No. There's a gap. It never hits what goes between those two horizontal lines. So what we have to do is look at how high does it go, and then say it covers everything from that point down, and then look at the top section and say how low does that U shape go? And then the range is everything from there up. Now, you could do second calc max or minimum to figure it out, but I think, especially if I put the line in there, you can probably tell how high does that bottom section look like it looks like it goes. Yeah, so the range here is everything from -1 down. That's the first part. Okay. So range, everything from -1, say it like this. That's everything from -infinity up to -1, or -1 down. Or, yeah, do you remember what it looked like? What's the next part? From the bottom of the U up.
It goes from 1 to infinity.
Yep.
Also on the first one, wouldn't it be a parenthesis for the...
Yeah, it should be just like I did that one. Sorry about that.
Oh, it's again.
So it's basically the opposite of the range of sine. Sine is -1 to 1. This is everything except -1 to 1. Okay, so there's my range. Let's do the vertical asymptotes. So vertical asymptotes for secant. What I'm going to do is go back to my table, find secant. Those are the 2 vertical asymptotes for secant. Am I doing any transformations to secant in this problem? No. Then I don't have to go through any of the steps that I gave you on slide 6, wherever that was. You guys have it right in your notes. But I don't have to do any of that because I'm not changing them. So pi over 2 and 3 pi over 2. Those are my asymptotes. But those aren't the only 2. There's millions of asymptotes. They go on forever. So what do I put on the end of each one of these to indicate that it repeats forever? And that's why I did this first, because you're going to need that right now. Yep.
Put period n for 2 pi.
So what's the period here?
The period is 2 pi.
2 pi. So if you add any multiple of 360 degrees or 2 pi to this asymptote, you'll get the next one of this asymptote. And the same thing here. You can shift that asymptote left and right forever, every 360 degrees or every 2 pi, and you'll get another one, either a cycle later or earlier. Okay, so last thing they want is the domain. Well, look at your graph. The domain is everything except the vertical asymptotes. And that's how we write it. Once you write the vertical asymptotes, the domain is everything except those dotted green lines. So let's put domain. All reals except the asymptotes. Yeah.
How would you write that if it was on like one of the tests?
Yeah, just like that. Yeah, there's no way to write it as like intervals because there's infinitely many. So we're just going to write it in words. That's the easiest way to say it. Okay, so that's secant. And let's finish up by doing the same thing for cosecant, and then that's I think that's a good place to stop. We're almost done anyway, but the last thing is just calculating intersections on the calculator, so that'll be a good, easy thing to start with tomorrow. Okay, let's do domain. Cosecant. What's the formula to find the period of cosecant?
T equals pi over 2. Right? No, that's the tangent.
Well, pi over b is the tangent.
Yeah.
Yeah.
2 pi over the actual value of b.
Yep. And what's the b in this case? Whoops. Sorry, I kind of misled you there. Period. What's the b in this case? Yeah. 1. I always do domain last. I think I wrote it first just because I saw it written first, but I do it last. Okay, so there's my period. Let's go look at the graph of cosecant to find the range. What's the difference between the range of secant and cosecant? Yeah?
There isn't one.
There isn't one. It's exactly the same range we just had. So range is going to be, hit it again, negative infinity to negative 1. 1 to infinity. So we got range, we got period. Are we doing any transformations to my cosecant? No. So then all I have to do is look up the asymptotes in the table. I don't have to set them equal to the argument. Because think about what would happen if you set 0 and pi equal to your argument. There's your argument. Well, 0 equals x, pi equals x. There's nothing to solve. If there was like a 2 or a number in front of the x, then we'd have to solve it. But there's nothing in front. So there's my vertical asymptotes. And how do we write the domain? Think about how we did it for the one before. Okay?
The domain.
Yeah.
I don't know.
How did we do it in the one before? Yep.
There's all wheels except asymptotes.
all reals except asymptotes. Okay, so tomorrow we'll look at how you find the asymptotes when you do shift it or stretch it. And then we'll finish up with using the calculator to solve equations. So there isn't much left. 352, let's see. Any sketching you can do on the calculator. You do not have to sketch by hand. And you can stop at 20. That's going to be part of tomorrow's nights. Stop at 20 for tonight. If you want to copy down the rest of it, you can, but you don't need to do that tonight.